Hi everyone. I have some time on my hands, so I thought I would go through section 7.5 of Stewart's textbook and solve every single odd-numbered problem. These are the ones with answers in the back of the book. I haven't looked at the answers yet. Hopefully I'll just get them right on my first try and I won't have to edit this video. But anyhow, yeah, I haven't looked at these problems aside from writing them down, and there's like 12 pages of them. But we're just going to go through, solve them all on the fly. Hopefully that's helpful. It might mean that there are some hiccups along the way. I might stumble at certain parts or do something incorrectly on my first try. But honestly, I think that's maybe instructive. And yeah, along the way I'm going to talk about my thought process. Since there are about 50 integrals here, I'm going to try to go very quick. Luckily, you have the opportunity to pause the video if you get confused about anything, so please do that. And last thing before we start, try solving these on your own before watching me do them. There's only so much benefit you can extract from watching someone do math. Math is very much, it's like an exercise, right? I don't go to the gym and watch other people exercise. You should very much actually do this yourself, and then just jump to the timestamp. I'll have them down below for whichever problem you're struggling with. I don't expect you to do all 50, but you can if you want to. Last thing I'll say, apologies if I'm a little congested. I think it's allergies. So, yep, you'll have to deal with that. But let's go ahead and get started. The first few problems here all have parts A, B, and C. First 4 problems, 1, 3, 5, and 7. And the point of these is that the integrals all look similar. Right? These all look pretty similar, these first 3. But the way to integrate them is supposed to be very different. So, okay, first integral, I look at this, I say, I see an x squared on the bottom, I see an x on top. This looks like a classic u substitution. Pick the denominator as u, that'll make du 2x dx. Or if you want to, solve for dx there, you can, or solve for x dx. Either way, I could just say, okay, I have a 2 in my du that I'll need to cancel out, so I can cancel that out with a 1/2, and then the integral transforms into just, 1 over u du. So this one's pretty quick. This turns out to be 1/2 natural log the absolute value of u plus some constant, don't forget that. And then I plug back in for u, right? So 1/2 natural log absolute value 1 plus x squared plus your constant, and we're done. So great, that one wasn't too bad. The next one we look at and we say, well, I can't do a u substitution because the x is missing from the top, right? For u sub, you need your the derivative of u to appear in the integrand as well, or at least something close to it. So I think about this one for a while, and then I say, oh, this is actually one I remember. This is just arctan, isn't it? Right, this is one you can memorize. If you don't have it memorized, then you could do a trig sub. You could have been like, well, take x to be, normally it's some number times tangent theta for something of this form. In this case, it'll be 1 times tangent theta. Then dx would have been secant squared theta d theta. And so the integral, if I wrote it out up here, well, let's just do it down here, would have been, okay, 1 over 1 plus x squared. That's now 1 over 1 plus tan squared, because x is tangent. The dx gives me this extra term, so let's put that on top. So I'll keep the d theta out here, and then this is secant squared theta d theta. But trig identities, the denominator is actually secant squared as well. So this turns out pretty nice. This just ends up being secant squared over itself. That's just 1, so that's the integral of d theta, which is theta, plus some constant. And just figure out what theta is. From right here, you could solve for theta. Say theta is, just take the inverse tangent. That's where the arctan comes in. So this is actually just arctan x plus c, as we wrote above. I might not always put parentheses around my trig functions, but there you go. or around the x in the trig function. Okay, so that's one you can either memorize or you can use trig sub for. The next one also almost looks like a trig sub. If there's a square root, that would be like arcsine, but there's not a square root. Yeah, so I can actually factor the denominator. If I can factor the denominator, it probably means partial fractions. So this is 1 minus x, 1 plus x dx. Right, it's a difference of squares, so it's just that formula. Okay, so let's do a little sidebar, I guess. Let's say 1 over 1 minus x, 1 plus x. If we remember the rules of partial fractions, we can say this splits up as, they're both linear terms, so you just get a constant on top of each of them. And if you multiply through by this denominator on both sides, then you get numerator equals a times 1 plus x plus b times 1 minus x. And then you can do the nice thing of picking good x values, right? So if x equals, let's try to cancel out the b term. So if x equals 1, that would give me the equation 1 equals 2a, which means a is a half. If x is negative 1, that'll cancel out the a term and get me 1 equals 2b, which means b is a half, which means this whole integral can be rewritten as, right, just plug in a half for a and b. This can be written now as a half over 1 minus x plus a half over 1 plus x, close parenthesis. And then we just get a couple natural logs from this, right? And you can take the time to check if you want to, right? Check that this actually worked correctly, cross multiply, get a common denominator, whatever you want to call it. I would get 1 half plus a half x plus another half minus that half x, and that just leaves me with 1 on top, and the denominator works out. So you can always check the algebra, and then for this, we have a sort of nice formula. We just get, the 1 half sticks around, then you get natural log of what's on the bottom. Same story over here, natural log of what's on the bottom with 1 half out front, and tack on a constant. Great. So 3 different techniques for 3 similar looking integrals. Future Troy here, I missed a minus sign in this, so just updating that. It comes from the fact that when you take the integral of this expression, there was a minus sign in front of the x. I missed it because, well, it's easy to miss. Usually I would have written this as like this integrand as negative x plus 1. And then it would have been more obvious, right? You have to sort of divide by the coefficient of x, so divide or multiply by negative 1. Next up on the chopping block is number 3. This immediately looks like a u sub, right? Pick u equals natural log of x, and you get du equals 1 over x dx. Don't need to correct for any constant factors. This just turns out to be u du, which integrates to u squared over 2 plus c. Plug back in for u. Let's write it like this. Natural log of x whole thing squared plus c. Done. Second one. You could do a u sub. You could also use properties of logs, I suppose. You could say this is the same as, a product inside a log is the same as the sum of the logs, so I could do this. Dx. Let's erase the parentheses, just make it look nicer. Log 2 plus log x. That turns out to be, well, integral of a constant is that constant times x. And you have to know the integral of log x. That one you can use integration by parts for. If you don't know it, try it out. It's just x log x minus x. Okay, so we got something like that. Let's check our answer. Let's actually do a u sub here as well, right? We have 2 different ways to approach this, so why not check, right? You could say u is 2x, so du is 2 dx. So I could say this integral, if I'm doing it the u sub way, is correct for that factor of 2 with a 1/2. And then this is just natural log of u du, which integrates to 1/2 times, same story, integral of u, or natural log of u is u natural log of u minus u. Then we plug back in, and this is 2x ln 2x minus 2x plus c. And they look different, but hopefully they're not. I mean, I could simplify our first one, right? These are both x's, so that's the same as natural log of 2 minus 1 times x plus x ln x. This one, when I simplify it, I get x ln 2x, because the 1/2 and the 2 cancel, minus x, because again the 1/2 and the 2 cancel, plus some constant. Let's see if that's right. I guess you could use properties of logs again and be like, this is log 2 plus log x. Split that piece apart, and does that work out to be the same? Let's see here. It should, right? I guess I could have combined everything. Everything has an x on it. This is log 2 plus log x minus 1. This is, factor the x out of this as well. Log 2, I say log when I mean natural log, plus x. Or, sorry, plus 1. Or, sorry, plus ln x. And keep the x out there. Yeah, so those work out to be the same. Written slightly differently, but there you go. Logs always end up looking different when you integrate something with a log, but you can work it out to make it look the same. Speaking of logs, here's another. X ln x. This definitely feels like integration by parts. Above I said you could use integration by parts to figure out the integral of log x. Here we're doing sort of one extra step, so I'd probably pick u equals x because I want it to get simpler when I differentiate, and then dv is just going to be everything else. To get, I'll write this once, that's sort of a derivative, this step will sort of be an integral, and I said, once again, natural log integrates to x ln x minus x, leaving off the plus c for now. And then the formula here should just be, this is uv minus integral v du. So let's plug in. uv is this times this. So I mean that gets kind of ugly, but whatever. At least it's not under an integral. And then the next piece is v du. So minus integral of that. Let's slide this down a bit. Okay. Yeah. Does that work out how I want it to work out? Maybe not. Maybe not, but maybe so. Let's write it down and see. So, yeah, we just get x ln x minus x dx, which is a little problematic, but you can probably make it work. This will be one of those fancy integrals. So let's write it like this. X squared ln x, all the terms outside the integral. And let's quickly kill this part of the integral, because that you can handle, right? Integral of x is x squared over 2. I won't need to worry about a minus sign because they'll cancel. So that'll be plus x squared over 2. And then I still have this minus the integral of x ln x dx. But that's okay in the sense that it appears on both sides of the equation. So the fancy trick is to move that over, right? Add that to the left-hand side. You get 2 times that integral. And that's just, this thing. x squared ln x minus, I guess I could combine these two terms. That's just minus x squared over 2 now. Plus c maybe. And then divide by 2, right? So this integral by itself should be half of that whole thing. I don't have to keep the constant in there. Whoops. It's an arbitrary constant, so whether I divide it by 2 or not doesn't matter. And there we go. This is one where I'm going to differentiate my answer and see if I messed up anywhere, because it's a tricky one. So take a derivative of... Let's just pull the 1/2 out, so I don't have to worry about it. I forgot to write an x here. X squared ln x minus x squared over 2. Okay, so keeping the 1/2, we need to do some product rule and whatnot. The product rule would look like front d back would be x squared times 1 over x, so that's just x. Plus back d front would be 2x ln x. And then derivative of the second piece is just going to be an x. So, I mean, that's nice. The x and the minus x cancel. And you're in fact left with the 1/2 and the 2 cancel, x ln x. Good. Okay, so that makes me happy. I think there may be other ways you can integrate by parts there successfully as well. So you might try some other techniques. See what happens. Huh. 2 problems done so far. Off to a slow start. But no matter. Let's keep going. Problem 5. So all of these sort of shout partial fractions to me. The only thing that changes between them is the number at the bottom. This one is actually plus 5, so they're all the same quadratic expression in the denominator except for the constant term. So yeah, a bunch shout integration by parts, but let's see if that actually works. Or sorry, partial fractions. Yeah, so this one, if I want to integrate by parts, I should factor the bottom. This looks like it factors like so. Because that's x squared minus 4x plus 3, yep. And so, again, little sidebar, minus 1. This should break up as a over x minus 3 plus b over x minus 1, which is the same as saying 1 equals a times x minus 1 plus b times x minus 3. And picking smart values, say x equals 3 and then x equals 1. X equals 3 would give me 1 equals 2a. So again, a is a half. X equals 1 gives me 1 equals negative 2b. So this time b is negative a half. So coming up here, this turns into a half over x minus 3 minus, because b was negative, this over x minus 1. And now it's quick. Right now it's, maybe this time I'll just pull the 1/2 out of everything and say natural log of the denominator on the left, natural log of the, sorry, that's a minus, natural log of denominator on the right. And then sometimes it becomes useful, this isn't just an algebraic simplification, sometimes it does become useful to write this using rules of logarithms. As such, a difference of 2 logs turns into a log of a quotient. But either way is technically correct. Sometimes this is a nicer form to work with if your problem is more involved than this, if it has bounds or something. But just an indefinite integral. Quick partial fractions. Next on the chopping block, can I factor this? Yes, it does look like I can, so it'll be another partial fractions. But this one's a little different because it factors like so. right? Feel free to check that. And since that term is repeated when I apply partial fractions, there's a little bit of nuance here. You get a over x minus 2 plus b over x minus 2 squared. Multiplying by that denominator gives me ax minus 2. Actually, should I even be doing this? I could just do a u sub for this, can't I? Yeah, I don't know if partial fractions is going to simplify this, but I guess we can see what happens anyway. I have a feeling a is going to come out to be 0 and b is going to come out to be 1. But yeah, let's see. Yeah, this would just be plus b. And then the only smart value to pick is x equals 2, which gives you b equals 1. And then a indeed has to be 0, yeah, because there's no x term. Yeah, so this is kind of silly of me to think to do partial fractions, but like I said, I'm doing this on the fly. The way I should actually have approached this is said, I can do a u sub. I could say u is x minus 2, du is dx. So this is the integral of just 1 over u squared du, which is the integral of u to the negative 2 du, which is u to the negative 1 over negative 1 plus a constant, and that's negative 1 over, when I plug back in, I get that. Cool. Yeah, so that was nicer. I didn't have to do partial fractions. Great. Let's see what's next. Plus 5. Can I factor that? Probably not. Not into something nice, at least. Right? Because they'd both have to be, both the constants would have to be positive or both would have to be negative, and that can't be the case if I want to work with integers, at least. So not factorable means different partial fractions. At least, maybe I can't do different partial fractions here. Again, if I try partial fractions, I think nothing will happen, right? Because this will just be like, oh, it's ax plus b over this, but it's going to probably work out that a is 0 and b is 1, so it doesn't change anything. So in that case, I think, can I complete the square on the bottom and maybe turn this into a trig sub? So I say, okay, completing the square, if I take this number, divide it by 2 and square it, so, and then tack that on, that would have been like saying, you know, this is, just add 4, and then plus 1, so that's no change, you're still adding 5. But then this can be, I mean, we just did that one above, right? That's x minus 2 squared. Yeah. And so I could write this whole thing as that. 1 plus, there's no square root or anything, so this probably turns out to be an arctan, actually, right? You could, again, do a u sub with x minus 2 as u. Du is dx, so this becomes 1 over 1 plus u squared du, and that is nice. That's arctan of u, as we saw before. Plug back in for u was just x minus 2, and that's what you get. And you could check by taking a derivative, right? Taking a derivative of that would give you 1 over 1 plus that squared. Yeah, which is exactly what you want. Okay, so that's a fun problem. Didn't end up using partial fractions for part B or part C, even though I thought we would have to. So goes to show you integration is tricky. Moving on, number 7. This is the last of this batch of like, ooh, look at these cool similar integrals. A looks like an easy u sub, right? You say u equals, or does it? I guess it doesn't look like an easy. No, it does. Yeah, u equals x cubed So du is 3x squared dx. Correct for that factor of 3 by putting a 1/3 out front, so it's just e to the u du now. So that's e to the u integrates to itself. And you get this. Plug back in for u. Done. All right, so not bad. Part B looks like two applications of integration by parts, right? Because you can take this as your u, differentiate twice to get it down to something nice. So two applications of integration by parts. Maybe I'll do the table method. So you write down u and dv. You repeatedly differentiate the left column, repeatedly integrate the right column. So x squared goes to 2x, goes to 2, goes to 0. E to the x dx, whoops, stays, e to the x. I'm not going to keep writing dx. And then you do this to get your answer, where you take, I'll put the positive over here, positive, negative, positive. So the answer here should just be, read it off as positive x squared e to the x, negative 2x e to the x, positive 2e to the x, and the rest will be 0 multiplied by stuff. Tack on your constant and you're done. Table method's awesome. Recommend you learn it if you haven't seen it. Yeah, so that one's done. Part C, let's see if that's tougher. Part C looks a lot like part A, except they flipped the 2 and the 3. So you can't pick that as u anymore. Of course, you can't pick this as u either, because you don't want a du in the exponent. Huh. Okay, this might be one of the ones where it's like a substitution followed by integration by parts. I don't see those very often, so we'll figure this out together. Yeah. I think a u sub works. Okay, so what I'm doing in my head is this. I'm saying let's actually try picking the exponent as u. Okay, so just go through the motions. That means du is this. And then the problem is, if I try to rewrite this integrand, you'd certainly get e to the u, but if I were to just write du here, I mean, where's the 2x coming from, right? So let's be like a little careful. Let's write it like this. Let's say this is, so before I do my u substitution, just to make it clear what I'm doing, let's write the integrand like that. Okay, weird. All I did was I, split up the x cubed as x squared times x, and I moved the x over to the right. Reason being, I'm going to do this. There's an x dx, so I can replace that with a half du. Maybe I'll keep highlighting. Here's x squared, that can be replaced by u. Here's another x squared, that can again be replaced by u. So it's a weird u substitution, but I think this will work. So you say this is now u e to the u du. And I forgot my 1/2. Now that is a classic integration by parts. Do I just want to do the table method again? You don't have to do, it's only one application of integration by parts, but why not? Take derivatives, take antiderivatives, match them up, plus minus. This should be, let's keep the 1/2 out front. This is u e to the u minus e to the u. Plus a constant, plug back in for u, and we're done. U is x squared, right? So that's x squared e to the x squared minus e to the x squared plus a constant. Ta-da! Okay, so that one was kind of fun. Let's move on to just mean integrals. So number 9. Doesn't say how to solve it. Let's figure it out. I see a sine and a cosine, one on bottom, one on top. I'm thinking u sub right off the bat. Always pick the denominator, because you don't want du in the denominator. This will give us du as negative cosine x dx, so I'll have to balance out a negative. Let's put that out front. And it looks like it's just 1 over u now. So that's negative natural log absolute value of u plus a constant. Plug in for u is 1 minus sine x, and done. Number 11. Oh, that square root makes it interesting, doesn't it? I wanted to say integration by parts. Can I still say that? Well, if I pick the square root thing as u, that would get kind of ugly, wouldn't it? Maybe this might be too complicated to do in my head. Let's just write it down. Would a u sub work? No. Maybe? I mean, sometimes when you see a square root, it's smart to pick it for the u sub. I guess I'll try it. I mean, it's not going to hurt. Here's the derivative of a square root of y. And then often with a square root problem, it helps to solve this for dy in the sense of, you know, multiply by a 2 root y. But root y is actually u. So this is 2u du. The problem is I wouldn't know what to do with the natural log. I mean, except I could solve this for y. I could say y is u squared. Okay, so I mean, let's write the integral and see how hideous it is. I won't write the bounds yet. I just want to write the integrand. Square root of y is u. Natural log of y is natural log of u squared. dy is 2u du. So let's put the 2u here. I'll just square that, du. Properties of logarithms. That square inside the log can come out. And that'll make it 4. 2 times 2. U squared log u du. And that looks like integration by parts, right? Set up your table. I mean, I hope it'll work. I think it should. Take derivatives, take... Oof. Do I want to do that? I don't really want to do that, do I? Because that's... You know, if I integrate, it's this guy. Well, I should use u. My bad. And I don't want to integrate that. That would be a nightmare. So maybe u sub is dumb. Let me copy this and then erase it in case I want to come back to it. So cut. Let's try integration by parts. So u is square root of y, dv is natural log of y dy. I could try flipping it. That may work better. Again, du will be 1 over 2 root y dy. And then v, natural log integrates to y ln y minus y. Then uv is ugly, sure. But, I mean, let's see. So uv evaluated at those bounds minus integral v du evaluated at those bounds. Looks like, let's just write it like this. Y square root of y, natural log of y, minus y square root of y from 1 to 4. Then integral v du looks like this. Maybe I'll pull the 1/2 out. So 1/2 integral 1 to 4. V du, I'm just multiplying these two things. So we get divide all the y's by square root of y. That leaves square root of y behind. Now, one of those I can handle quite well, and the other I can also kind of handle. Yeah, so I think this will work. Right, I think you can solve the indefinite integral first and say, again, the trick of like this appears twice. I really don't want to do that again, so I'm not gonna, but I mean you can. What I'm going to do instead is see if flipping these works. So u equals natural log of y, dv equals square root of y dy. Then differentiating natural log gives me 1 over y, which is nice. Integrating y to the 1/2 is y to the 3/2 over 3/2. So that's 2/3 y to the 3/2. And then this works out much nicer when you do your formula. Okay, u times v is just 2/3 y to the 3/2 natural log of y from 1 to 4. And then v du is really nice. You just get 2/3 square root of y. I'll write it as 2/3 y to the 1/2. Great. Let's just leave this alone for now. Again, that integrates to y to the 3/2 over 3/2. So you get another 2/3. 2/3 times 2/3 is 4/9. And then that's y to the 3/2 with that plugged in. Now we can plug in. Oh, it's going to be ugly. 2/3 times, okay, y to the 3/2. If I plug in 4, well, the 3/2 is to the 3rd power and then take a square root, or vice versa. Take a square root and then raise it to the 3rd power. Square root of 4 is 2. 2 cubed is 8. So that's 8 log 4. If I plug in 1, I get 0. So no worries there. Then this is minus 4/9. Again, y to the 3/2 is 8. This time you do care about the lower bound. Y to the 1 to the 3/2 is just 1. So you get whatever that is. I'm not going to simplify it. Okay. Hopefully it's correct. Number 13 looks like a really nice u sub. U is natural log of y, right? Because I'm just thinking I already have a 1 over y times dy in the integrand. So this becomes natural log of u du. And we know what that integrates to because we memorized it, or you can use integration by parts, and then you plug back in for u. So this becomes natural log of y times natural log of y minus natural log of y. Really ugly, but there you go. It's a weird one. But that looks right. Okay. 15. Not a u sub. Right, I would have to pick x. Oh, well, I guess I don't have to pick x to the 4th. Yeah. Okay. Sort of a big strategy in mathematics in general is looking at a problem and saying, what do I hate about this problem? And what would make it look nicer? And all I'm thinking right now is like, man, this would be sweet if that was a 2. So I think to myself, how do I make it a 2? Why not do a u sub where u is x squared? You'll have to do du as 2x dx, but let's see what this transforms into. The 2 has to be canceled out with a 1/2. Then you have x dx, and then this is u squared plus 9. That's much nicer. That integrates to some kind of arctan thing, right? That's one, again, you can either memorize or you can do a trig sub for. I won't spend time doing the trig sub, but you can sort of memorize that that's, whatever the number is, you do 1 over the square root of that. So 1/3 arctan And then arctan is I guess, the variable divided by that same number. It's a constant. Cool, so 1/2 times a third is a sixth. And then plug back in for u. U was x squared, so that's x squared over 3. And let's check that. You know, if you took a derivative, that would give you 1/6. Arctan differentiates to 1 plus whatever squared. Chain rule says I need to multiply by the derivative of that, though, so by 2/3 x. The c, of course, doesn't matter when I differentiate. And then if I work that out, you get a 2 on top when you multiply all those fractions. A 2x, I suppose. On the bottom, you have a 6 times 3 is 18 plus, that's x to the 4th over 9 times 18 is 2x squared. Factor a 2 or cancel a 2 out of everything. That's x over 9 plus x squared. That works. Wait, does it work? That was x to the 4th, sorry. Cool. Still fine. Yep. Good. It works. Sorry. It was behind me. Apologies. Getting used to this new camera setup. Okay, let's try not to lose steam. Let's keep on chugging. Definite integral. I see a quadratic on the bottom. I'm hoping I can factor it and do partial fractions. Does it factor? X minus 1 plus 4? Yeah, it works. Unfortunately, the top term doesn't cancel, so it's a little ugly, but whatever. X minus 1, x plus 4 is good. Then you say, do my partial fractions. It's a really nice one. You don't have any quadratics or repeated terms to worry about. That's just a over x minus 1, b over x plus 4. X plus 2 equals a times x plus 4 if you multiply across, plus b times x minus 1. Pick x equals 1, and you get 3 equals 5a. So you get a equal, I hate ugly numbers, 3/5. Plug in x equals, what, -4, I guess? And you get -4 plus 2 is -2. -4 minus 1 is -5. Oops, that should be a b. So b is 2/5 positive. Cool, so this becomes integral from 2 to 4. 3/5 over, that's our a term. This is our b term, 2/5 over x plus 4. Integrate again, super nice, except for the 3/5 and whatnot, but it's just natural log of what's on the bottom. 2/5 natural log absolute value of what's on the bottom. Cool, plug in 2 and 4. Let me check the algebra really quickly and make sure that actually works. 3/5 plus 2/5 x is x. 12/5 minus 2/5 is 2. Yeah, that does work good. I mean, it's hideous, but just whatever it works out to be. You guys can plug in numbers, right? I don't want to plug in numbers. We did the calculus. It's done. Next problem. This looks like trig sub. Probably no way around it. No u sub can do it. So, okay, I see x squared minus 1. I think that's like a secant type trig sub. In particular, you do x equals secant theta. So dx derivative is secant theta tangent theta d theta. So this becomes the integral of a whole big thing. Big thing. Dx gets replaced by secant theta tangent theta d theta. X cubed becomes secant cubed. And then the square root becomes secant squared minus 1. Okay, remember your trig identities. Secant squared minus 1 should be tangent squared. Tangent squared under a square root is the absolute value of tangent, but just forget the absolute value. So this will be, yeah, this is pretty nice, right? Secant theta, tangent theta, I'll just keep that the same, over secant cubed theta. And like I said, square root of tangent squared, we're just going to call tangent. You get a ton of cancellation, though, and you're left with the tangents go away, one of the secants goes away, you get 1 over secant squared. If I ever see, just an ugly trig function by itself, I write it back in terms of sine or cosine. So that's 1 over secant is cosine, so that's cosine squared. And that's one you can handle with a trig identity, if I remember it. So it should be 1/2 1 minus cosine of 2 theta. I could figure this out if I did some complex, but let me just look it up. I'll pause the video. It's plus. Okay, so it's plus here. I always forget that. Anyway, integrate as usual now. 1/2 integral of 1 d theta is theta. Integral of cosine of 2 theta, you could do a u sub, but you could also just get away with being like, pull a 1/2 out, integrate cosine. Ta-da! Plus c. Then, of course, the ugly thing is I don't want an answer in terms of theta, I want it in terms of x. So I say to myself, how can I build a triangle that matches this situation? Let's say theta is here. If I want x to be equal to secant theta, well, secant is 1 over cosine. Cosine, if you think SOHCAHTOA, is adjacent over hypotenuse. So this should be the reciprocal of that. Hypotenuse over adjacent. Should be like x over 1, basically. So hypotenuse over adjacent. Do Pythagorean theorem, and you get that, which matches this, which is a good sanity check. And all I need is sine of 2 theta. Let's actually do another trig identity, because I don't want to deal with sine of 2 theta. I'd prefer to deal with sine of 2 theta is 2 sine theta cosine theta. The 1/2 will cancel the 2, so it's just sine theta cosine theta. And we can read off the triangle now. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So that's this and this. Great. And then theta itself, you could just say, from here, take arcsecant. Not something you see very often, but there you go, arcsecant of x. And then just plug those in, right? So this is 1/2 arcsecant x. Sine was this thing. Cosine was this, plus a constant. And then, I really hope that's correct. I don't feel like taking a derivative to check. Who remembers what the derivative of arcsecant is? Not me. Okay. I'll check it after. Future Troy here, silly mistake. This final answer at the bottom, this should be multiplication. Right, just from the fact that sine and cosine were multiplied together. I got a little plus happy in this video. Next one. Yeah, we're into the trig section. Time to hate our lives. Cosine cubed over cosecant. I don't like cosecant. Cosecant's 1 over sine, so this is cosine cubed sine. And that's just a u sub, right? Pick u as the thing to a power. Well, not the whole thing, but just the thing that gets raised to the power. Then you'll have a negative sine x dx for your differential. So you correct that negative sign. This just becomes u cubed du. So that's u to the 4th over 4. Plug back in. U was cosine, so it's cosine to the 4th. That was nice. Okay, maybe we don't hate our lives too much. after that one. Next one, though. Well, whenever I see secant tangent, I think that's the derivative of secant. Does that help me, though? Maybe if I integrate by parts or something, because we have the x out front? But no, then I'd have to integrate secant tangent, and I don't want to do that. Unless you swap it? That seems weird. Let's see what happens if we swap it. If we say u is... Wait, no, I do want to integrate. What am I saying? Okay, so yeah, pick u equals x. So the derivative of u is just dx. Then dv is the remaining part, secant tangent. Yeah, I was just doing it backwards in my head. The integral of secant tangent is secant, right? Because you know the derivative of secant is secant tangent. So great, you get that. This should work out pretty nicely now. uv is x secant x minus the integral of v to u. Well, the integral of... that just turns into secant. And again, this is one you can memorize. This is log tan x plus secant x. There are some really ugly ways to figure that out. Actually, there's one really beautiful way to figure that out, but not really for this video. Let's just pretend we've seen that already. And go on to number 25. So 25 is probably another integration by parts, because I see the t floating out here, so I'm like, pick that to be u, because that gets simpler. dv is the rest, and we have sort of already seen how to integrate cosine squared. In particular, you use this trig identity that was like right here, if you were watching problem 19. So like just as a sidebar, let's do that again. Trig identity is 1/2, I'll get it right this time, plus cosine 2x, or 2t, dt, and that integrates to 1/2, so theta plus 1/2 sine 2t. No need for parentheses, I guess. Plus a constant, but we won't use that. Let's just write it here. And see if this works out okay. Why did I put a half there? Yeah, no, that's right, that's right. Good. Sine 2t. So uv is ugly, integral v du is also ugly, but it works. So u times v... Wait, why is there a theta? Apologies. It's late. Theta should have been t. Okay. Cool, that looks better. Yes, it does. Okay, uv is 1/2. Multiply by t, you get t squared plus t over 2. God, this is ugly. This might be one I don't plug in the numbers for. 0 to pi. Integral 0 to pi. This will be integral v du is, let's pull the 1/2 out. So just integrating t plus 1/2 sine 2t dt. Okay, maybe this doesn't work out to be too bad, actually. Sine of 2 pi is 0, sine of 0 is 0, so that second term doesn't actually matter. So plugging in there, you just get 1/2 times pi squared minus 0, so 1/2 pi squared, just pi squared over 2. Don't see pi squared a lot, that's fun. Then this integral turns out to be minus, keep the 1/2 out, just to make it easier. Integrate t to t squared over 2. Integrate, I guess this will be minus when I integrate the sine term. So it already has a 1/2. We'll get another 1/2 by u sub or whatever you want to call it. So it'll be 1/4. Then cosine 2t. Cosine's a little meaner at 2 pi and 0. I mean, it's just 1, but it's not 0. So, but let's finish it, because we started it, so why not? 1/2. So plug in pi, you get pi squared over 2. Plug in pi to the cosine, you get, okay, cosine of 2 pi is 1, so that's -1/4. And then you subtract what you get when you plug in 0. Well, that's 0 for this term, and 1/4 for that term. So I guess that works out. That's minus a -1/4. So some terms cancel. You get pi squared over 2 minus pi squared over 4 is pi squared over 4. That worked out better than I thought it would. Assuming it's correct. Again, I haven't checked. Okay, 27. Let's talk about this one. This is one I have seen before, so I'm sort of prepared for it. If you're not prepared for it, it's not immediately obvious what to do. You might think u sub, but there's no, like, what do you do? Maybe you pick this for u, but then where's the derivative going to come in, right? You need a 1 plus e to the x then. Maybe you pick just e to the x, but then what do you do with the x? The trick is to rewrite this before you do anything. Use rules of exponents. So e to the x, and then plus turns into like multiplication, so it's e to the other exponent. Don't often see e to the x, but there it is. And now you can actually do that u sub. You could say u is e to the x, so du is also e to the x, dx. And what do we have? We have e to the u here. This is an extra just term of u. Actually, I mean, you could call it, it's probably safer, call that du. Right, so this is the integral e to the u from this piece. And then the highlighted region is just du. So that's just e to the u plus c. Plug in for u. Much nicer than expected. And you can check, take a derivative. Chain rule is required, but you get e to the x times the derivative of the exponent. And then rules of exponents get you back to where you started. So works out. Apparently 29 was missing when I recorded this, so here goes. Arctan square root of x makes me think, I mean, whenever I see square root of x, I think do a u sub with that. Let's see if I can fit this all in here. 1 over 2 root x dx. Probably solve this bad boy for dx is 2u du. Yeah, and then the integral becomes equals arctan of u. And then I can replace that dx with 2u du, so times 2u du. And looking at that, I'd probably need integration by parts. So maybe I pick, again, let's do the table, 2u as the thing I repeatedly differentiate, and then arctan over here. Actually, do I want to integrate arctan? Maybe not. That's okay. Let's try it the other way around. Since I don't want to integrate arctan, at least arctan has a nice derivative. It's usually not the right strategy to do it this way, but maybe it will be. Derivative of arctan u is 1 over 1 plus u squared. Integral of 2u would just be u squared. Yeah, so let's write out what this would look like. I guess it's not gonna get nice using the table method, but anyway. Basically I'm saying this is like my new u. I'll put a little tilde over it to differentiate it. And then this is like dv. Why not put a tilde over that too? And if we do that, uv is going to be u squared arctan u minus the integral of v du. So the integral of v, which is our u squared, du. So u squared derivative of arctan is 1 plus u squared. And whoops, it's hidden, but there you go. And then this one should be doable. I mean, there are a couple ways to tackle it, but I would sort of rewrite the integrand as sort of 1 plus, or the numerator is 1 plus u squared minus u. So I added 0 by putting 1 and minus 1 in there. And then this splits up as the integral. So these two terms together give me 1, and then minus 1 over 1 minus u squared. So that becomes that. And yeah, that one's not bad, right? Then overall, the answer you get, we get our u squared arctan u. Let's plug back in for x. So u squared is square root of x squared, so that's x. Then arctan of u becomes arctan square root of x. Minus this integral. Let's write out what that is. Integrate 1 with respect to u, you get u. Integrate 1 minus, 1 over, this should have been a plus, 1 plus u squared, and you get arctan back. U plus c. I meant to put that down here. Sorry, brain is very fried. And so you get minus, plug back in for u in both of these places. U is square root of x. Minus arctan square root x. Put the plus c out here. That should be your final answer. Okay. On to 31. 31. I saw this one when I was writing it down, and I thought to myself, that would be annoying to FOIL out. Some like binomial thing to an 8th power. I mean, you could do it if you want. I don't really want to. Whenever I see something to an ugly power, I think u sub. Right, I think just make the thing in parentheses u. And you'll be like, but wait, that makes du ugly, right? Ugh, and then what do I do with that? But if you remember the other problem I showed you that had a square root, just multiplying across by 2 root x, in other words, solving for dx gives you dx equals 2 root x du, which is sort of a nonsense thing. I don't want x and u's floating around at the same time. So how can I get everything in terms of u on this right-hand side? Well, this root x is u minus 1. Right? Solve this for root x. So why not put u minus 1 here? Now, like I said, I only glimpsed this when I was writing it down, but I think this will work. Now, since we're doing a u sub, I should be careful and be like, well, x was initially 0 to 1 based on these bounds. So plug that in to this expression. U would start at 1 plus square root of 0, so just 1. And you would end at 1 plus square root of 1, which is 2. Cool. So our bounds change to 1 to 2. And let's see if we can actually write this integrand down. So 1 plus root x is u. And we're raising that to the 8th power. That gives me this. And then I just have to write down what dx is, right? That's the only piece I'm missing. But dx is just right here. 2 times u minus 1. So times 2u minus 1. Let's write this nicer. Let's pull the 2 out. Integral 1 to 2. I don't need parentheses. What am I thinking? Let's keep it nice. Put the parentheses here. U to the 8th times u is u to the 9th. And then just minus u to the 8th. And then that should be doable. Right, this is 2 This becomes u to the 10th over 10 minus u to the 9th over 9. Plug in your bounds. And I mean, it's not pretty, so I'm not going to plug them in, but feel free to finish it for me, as I often say. And we just hit the 1 hour mark. We're like a third of the way through. I don't know why I'm torturing myself. Let's try to go faster. This one. Yeah. Maybe? Often, like, a weird u-sub will work. So pick the denominator. But then what do I write for 1 plus 12t? I mean, I guess I could say 1 plus 12t is like 1 plus 3t plus 9t. This piece is u. Oh, but that's really ugly. I mean, I guess I could do that. I guess I could say that's 3u minus 3. I don't really want to do that. Is there a nicer way? I guess the other way to get a 12t from a 3t is multiply by 4. So that's 4u. Except 4u is actually 4 plus 12t, so subtract 3. Huh. Okay. Check that that's right. You know, plug back in for u and see that it's a correct statement, but it looks correct to me. Yeah, that's good enough. So we balance out the 3 here with a 1/3. This integral also has bounds. Let's not write them yet. The top is going to be, well, 1 plus 12t is 4u minus 3. The bottom is just u. Yeah, that works. And u, you know, initially t was 0 and t went all the way up to 1. If you plug those values in, you get u equals 1 to 4. So this is 1 to 4. Then I probably just do this. Simplify the integrand whenever you can. Split it into 2 fractions in this case. 4u over u is just 4. And then minus 3 over u. So this is 4 integrates to 4u. U is my variable. 3 over u integrates to 3 log u. Log absolute value of u. Plug in 1 and 4. And maybe I'll do it this time. This gives me 16 minus 3 log 4. And then if I subtract what I get when I plug in 1, well, log of 1 is 0, so that term doesn't matter, but this term does. Yeah, so you get that. That simplifies even more. 16 minus 4 is 12, divided by 3 is 4. 1/3 times 3 here is just 1. Surprisingly nice. Huh. And hopefully correct. Number 35. Well, that looks like a problem. That does look like a problem. I don't like that. I would like it if it was like... Is this one where I can multiply by... Can I do like the conjugate trick? We're starting to get into the hard ones if you can't tell. Can I multiply by 1 minus e to the x? Right, so this would be 1 minus e to the x on top. And then you get a nice difference of squares. That's 1 minus e to the x squared, or 1 minus e to the 2x. Is that better? I'm not sure. Can I do a u sub at this point? Not that I'm seeing. But, oh, no, this might be another sneaky U sub. Apologies, it took me a second. What if you did try this as U? So du is e to the x dx, which means dx, is this going to work? Maybe? I mean, dx is e to the negative x du. E to the negative x is 1 over e to the x. But e to the x is, solve this for e to the x. E to the x is u minus 1. Oh, that doesn't look good. But maybe? Right, so this integral transforms into 1 over u. And then dx is just this guy, so I need to put that. Oh my god, it works. That's absurd. Okay, so you have the u from before, and then you have the u minus 1 from here. You have the du from there as well. And then that's partial fractions. Wow. Okay, so let's do it. Oops. Do I just remember this one off the top of my head? Can I just say partial fractions gives me 1 over u minus 1 over u minus 1? Or plus? Because that would be u minus 1 minus u, and that's a negative 1. Do I have to flip it, or is it plus? I think I flip it. Sorry, you can do the partial fractions. It's really quick. I just feel like this is right. Because that's, if I get back to a common denominator, it's u minus the quantity u minus 1, which is positive 1. So that's good. Okay. Then you integrate and get natural log absolute value of the first denominator minus natural log absolute value of u plus c. Why not write it nice? U minus 1 over u. Which is actually even nicer. U over u is 1, and then minus 1 over u, if you split that fraction apart. Plug back in for u, don't forget your constant. 1 minus 1 over, what was u? U is 1 plus e to the x. So weird, worth checking. Let's forget about the absolute values. C doesn't matter, of course. 1 over 1 minus 1 over 1 plus e to the x times the derivative of that mess. Oh god, okay. Derivative of that is going to be, what, just this squared? And it's now positive? Right, because chain rule or quotient rule or whatever you want to do. Times the derivative of that. Give me an e to the x. Sorry, I'm not explaining much. I'm trying to go fast. Does that work out, is the question. You get e to the x over 1 plus e to the x squared minus one of those cancels in that fraction there. 1 plus e to the x. And I mean that's e to the x over 1 plus e to the x appears in both of those. So that's 1 plus e to the x minus 1 if I factor it. But then those cancel, and you're left with that. It does work. I didn't make a mistake. Wow! That's a wild one. Let's see how much further I can get. 35 was tough. Wait till we get to like 93. 37. Who knows? I I mean, if I see a square root of x squared minus 1, I'm thinking trig sub, but what about this natural log, right? Ugh. That can't work out nice. I can't do a u sub. Because, like, everything's inside the natural log. I don't want du inside the natural log. Am I really going to do a trig sub? I guess. Again, okay, x equals secant theta will work here. So dx is secant theta tangent theta. I mean, let's just see what happens. Need more room. This will be natural log of, okay, we said x was secant. Then, let's just be quick. Square root of secant squared minus 1 is the square root of tangent squared, which is just tangent. And then you need the dx on the end. God, this looks bad, doesn't it? I mean, what do you do there? Right? Wait, oh, wow. Does that work? I mean, now I'm looking at this and I'm seeing lots of things that look like integrals I know. So I'm thinking integrate by parts. Because secant tangent's the integral of secant. Natural log of secant plus tangent is the integral of secant, basically. I meant to say derivative for the other one. But yeah, that might work. Wow. Okay. So you want to pick u to be the thing you can take a derivative of. No. No, that doesn't work. Or does it? I mean, who knows? Maybe it'll work. So integrate by parts. I mean, integration techniques are just throw everything at the wall and see what sticks. So take a derivative of u. It's going to be ugly. 1 over that thing times derivative of that thing, using chain rule. Derivative of secant is secant tangent. Derivative of tangent is just secant squared. Actually, no, I can't simplify that. That's fine. I can almost do it. I don't think this is going to work, but whatever. Because I'd have to integrate that. The nice thing would have been, you know, dv would then have to be secant tangent. And then you're like, that integrates super nicely. But the question is, can I integrate what I get if I multiply these two? I mean, the answer is like a big fat maybe. Right? Maybe. Who knows? Who knows? Who knows? Who knows? Whatever. We'll try, right? It's worth a shot. So this... Let's just scoot this over here. Make it small. Apparently this would be uv. So that's secant theta natural log secant theta plus tangent theta. Sure, there's an easier way to do this. Minus the integral of v du. Okay, this is awful. This can't be right. Secant squared theta tangent theta plus secant cubed theta still over secant plus tangent. I mean, can that be right? I mean, maybe a u sub solves it. Maybe now you're like, okay, I'll do a w sub because I've used so many other variables. Pick the bottom. Right, dw would have been secant theta tangent theta plus secant squared theta. But that's basically the top. Except the top has an extra factor of secant now. Can I make that work? Oof. Ugh. Maybe not. Sorry, my video's blocking it. Because that's 1 over w dw, but it also has a secant. Secant theta is w minus tangent theta, but you can't really write theta nicely. Or w nicely. Crap. Okay. That was a lot of work for nothing. What are my other options? Again, I'm going to erase this, but keep it in case I need to come back to it. Cut. I don't know. Let's try something stupid. Let's be like u sub where the whole thing is u. Sometimes that works. Du would be 1 over that. Times derivative of that. I'll put that on top. Derivative is 1 plus... Oof. 1 over 2 times that square root times 2x. So I guess the 2's cancel. It's just 1 over that square root. Is that right? 1/2 comes down, put it in the bottom, times 2x. Oh, I missed the x. Okay. I mean, is this actually what I'm trying right now? I mean, yeah, it is. Let's just see what happens. Let me simplify this first. The top, let's get a common denominator. So the top is x. Oh my god. This might be a miracle. Okay. Keep the bottom the same. Dividing two fractions flips it, and so much cancellation happens. These both cancel, and you get this. I mean, I forgot my dx. I'll just put it there. Is that acceptable? Not quite. Can we make it acceptable by fiddling with u? Well, I want to get rid of the natural log, so, you know, e to the u would be this. Oh, is this not going to work after all? Oh, that would be so upsetting. Right, because this would give me... I sort of want to solve for this piece. But that's e to the u minus x, which isn't useful unless I solved for x in terms of u. Oh, that's maddening. That's so close. Did I mess up anywhere? E to the u. Wait. No, e to the u minus x. Oh, that makes... That was so close. Huh. So trig sub didn't work, u sub didn't work. God, what else is there to tackle this? Integrate by parts? uv minus integral v. Wow, okay, integration by parts might do it then. So sorry this is taking so long. I should just leave that. That's still going to be u, but now I integrate by parts and say dv is the rest of it. And the formula for integration by parts should give me, I'm so sorry this is cluttered, uv, so I suppose I don't need this anymore. Yeah, but the rest is good. So uv is x ln x plus root x squared minus 1 minus the integral of v du, right? So those two pieces, and you get a u sub out of it, right? You integrate this guy with a u sub, you say, again, I'll do a w sub, x squared minus 1, dw is 2x dx, so you cancel out a factor of a half. Can't believe this. So we cancel out the 2 with the 1/2, and then this is just, this is just square root of u du under the integral, which goes to u to the 3/2 over 3/2. And then you plug back in, and you get your answer. And I'm not going to check this one, because that derivative would be hideous. The 2's cancel. U is x squared minus 1, or I guess that's a w technically. But w is x squared minus 1 to the 3/2 plus c. Oh, seems correct. Totally absurd, but there you go. Future Troy here. It turns out I messed this one up pretty catastrophically, just on the algebra. In red is the correction. This should have been 1 over that square root. Apologies for that. If I plug that in, we can actually see what we get, right? We're still doing integration by parts, but now when I do the whole, integrate v du piece, which is right over here, instead of that, let's just erase. I wrote what the answer should have been here. That's the only change. This should be, so v du, so x over that, not x times that. But it works out nice either way, right? So you still do a u substitution here. And when you do that, maybe you can still use this, right? So we're calling it a w substitution. It still works, it's just that this integral becomes, okay, let's rewrite this. And the integral becomes, again, you need to factor out the 1/2. And then this is u to the, or w to the negative 1/2 power. Negative 1/2 dw. Looks good. And then when I integrate that, I get sort of a 2 root w. And the 2 cancels out with the 1/2. So you just get a root w, where w is x squared minus 1. So there you go. Sorry for the mistake. How much longer am I going to survive? Oh, this marathon. Okay, 39. This one looks doable, actually. Right? Maybe? It feels like a multiply by a conjugate type thing, especially because there's a square root around. That would get me, that would be a little messy. Might work. Is there a better strategy? Before I try that, because that one's going to be ugly, what if I did a u sub? So u is, no, I can't really do that, because there's the square root, right? Yeah. Well, no, I mean 1 plus x would be negative u would be negative 1 plus x, so plus 2. So is that 2 minus u? Yeah. But that doesn't get me anywhere, that's, or does it? right? That would transform this integral into this. 2 minus u on top, u on bottom. Include a negative sign for the du. But that's pretty ugly, right? Yeah. So that's ugly. Instead, you might say what I was saying before, of do something like this. Basically, like, multiplying by a conjugate is nice whenever you see something that you would love to be squared, but it's not. So I probably want this to be multiplied by 1 plus x over itself. Totally allowed, because it's multiplying by 1, basically. Okay, and that would be this. Let's write it as one big fraction. 1 plus x quantity squared is 1 plus 2x plus x squared. On the bottom, you get a difference of squares, and it's just 1 minus x squared. I think this one is... Oh, but it's all under square root. Do I like that? Sort of? Okay, sort of. The square root is... Right, let's write this back as just 1 plus x times itself. So this would have been 1 plus x over square root of 1 minus x squared. And maybe a u sub works now. Yeah, okay, you split this in two fractions, right? So 1 over 1 minus x squared under the square root. And then I'll split it into two integrals, why not? One of them's a u sub, one of them is just arcsine. Right? You might recognize 1 over the square root of 1 minus x squared as the derivative of arcsine. So the integral is just arcsine. And then this guy is a u sub, right? Come over here, be like that's, if you let u equal 1 minus x squared, you need to cancel out a negative 2. So you're like that piece is negative a half. U over, or 1 over the square root of u, du. It's u to the negative 1/2 du. And that integrates to u to the negative, or u to the positive a half divided by positive a half. So actually the halves cancel. And you just get that. So that should be minus square root 1 minus x squared plus c. That's nice. Kind of surprised that works out, but there you go. 41 immediately shouts complete the square right at my face. In the sense of 3 minus 2x minus x squared is, I want the x squared out front, so let's just pull out a negative and say that's x squared plus 2x minus 3. First of all, can I just factor that? That would be, I would need like a minus 1 plus 3. X minus 1, x plus 3. So I could put that under the square root. I don't really want to do that. I want to complete this square instead. But I was just checking if that would work. I don't think it would. So let's actually complete the square. This would be negative. I'm going to square something and then add something to it. The thing, you take the middle term, the 2x, so that coefficient 2 divided by 2, you get 1. Square that, you get 1. So this should be x plus 1 squared. Would be x squared plus 2x plus 1. But I want the minus 3 out back, so I subtract 4. So completing the square gets me that. Let's factor the negative back in, so that's 4 minus x plus 1 squared. And feel free to check that that actually works out. It does. And so I could write this that way. This should still be under square root. 4 minus x plus 1 squared dx. whenever you see something other than x being squared, you probably want to do a u sub. So we say u is x plus 1, du is dx. So this just becomes quite nice. Square root of 4 minus u squared du. And I mean, that you probably need a trig sub for. So this is testing like many of our techniques. It's not 1 over that, so you don't get arc sine right out of the gate, but you could definitely do, you know, u as 2 sine theta. Is that right? Yeah, 2 sine theta. Du is 2 cosine theta d theta. So this becomes the integral, lots of substitutions, of square root of 4 minus 4 sine squared with an extra 2 cosine theta because of the du. Now I can pull a 4 out of both of those, but it's under square root, so it's really like pulling a 2 outside of everything. And there's another 2, so 2 times 2 is 4. I'm asking you to do some work in your head, but when I pull out the 4, I'll have 1 minus sine squared, which is cosine squared. Under a square root is cosine, and then you have another cosine, and this works out. Right? Again, we have to use our little formula here to solve this integral of cosine squared is actually 1/2 1 plus cosine 2 theta. But once you solve that, okay, you get a 2 here, theta plus half sine 2 theta, we've done this one a few times, plus a constant, and then you have to just undo everything, right? So the theta has to be turned back into u, and then the u has to be turned back into x. The theta can be turned back into u with a triangle, right? You want u to be 2 sine theta. So you're saying, you know, you want sine theta to be u over 2. But sine is opposite over hypotenuse. So you're like, that's u, that's 2. Pythagorean theorem gives me this, which matches up with this, which is good. Yeah, and then all that's left to do is say, so this is 2. You can solve for theta here, right? That's arc sine of the thing on the right, u over 2. So this is 2 arc sine u over 2. Here the 2 and the half cancel, but I don't want to do sine 2 theta. I would prefer to do sine 2 theta is 2 sine cosine theta. So the 1/2 will cancel that way anyway, so the 2 sticks around. Okay, I need to convert that. So sine of theta we know is u over 2. Cosine of theta is opposite over hypotenuse, or sorry, adjacent over hypotenuse. So that comes out. And then u was x plus 1. So whew, it's a beast, but you get there in the end. Instead of u over 2, it's x plus 1 over 2. The 2's cancel here, but not there. So that's plus, call it x plus 1 square root 4 minus x plus 1 squared. And you still have 1, 2 hanging around. I mean, I think that's right. Again, I haven't checked, but hopefully all that work was not for naught. Let's go on to 43. 43 also scares me. I see a cosine squared, but it's not 1 minus cosine squared. Right? 1 minus cosine squared would be sine squared. Maybe I can plug in a half 1 plus cosine 2x. Oh, but then in the bottom I get 3 halves plus 1 half cosine 2x. And I can't do a u sub there, so that's not useful. Oh, this one's a thinker. Definite. Okay. Thought just came to me. Definite integral with symmetric bounds. This might be the one of the ones where we don't integrate anything, and this just turns out to be 0. You would just have to check if this function's odd, which it kind of looks like it. Right? To check, you would say, what's f of negative x? Well, it would be negative x over 1 plus cosine. Cosine squared is really cosine whole thing squared, right? So it's like that. But that is negative x over 1 plus, should have closed the parenthesis. Well, cosine itself, let's be a little careful here. Cosine's even, so cosine of negative x matches up with cosine of x. So this is just negative x over 1 plus cosine squared. But that's exactly negative f of x, if you make this negative. Yeah, so this is odd, which means this is 0. Okay, I'm glad I didn't have to integrate that. Right, we just have to know that it's symmetric about the origin, and you have symmetric bounds. So negative area cancels positive area. This one, no such luck. We just have to tackle it. Let's think. We need some trig identities. I don't want to plug in secant squared as a trig identity, do I? Do I want to plug in tan squared? Tan squared plus 1 is secant squared, so tan squared is secant squared minus 1. It might work. Let's see. So this is 0 to pi over 4. Yeah, we're doing something like this. Save one tangent, and then tangent squared, I just said, was secant squared minus 1. And you still have the secant squared out here. And then we ask if this looks nice enough to integrate. It might not, but who knows. Distribute, you get tan theta secant to the 4th theta d theta. And then you can just split into a second integral. The other term is minus, so I pulled the minus out. Tangent secant squared. Okay. Yeah, this looks doable. This looks really doable, actually. So what I would do is I would say write everything in terms of sine and cosine. Tangent sine over cosine, secant's 1 over cosine. So this is sine. That comes from the tangent. And then we have a cosine on the bottom from the tangent and 4 cosines. So in total 5 from everything else. That looks like a u sub. And the other one also looks like a u sub. Actually, I think there are 2 different ways you could do this u sub. Because derivative of tangent is secant squared, so you could call this, I'll just go ahead and write u du, where here we're letting u be tangent. Du is secant squared. Right, so that's u du. Just be careful. Initially, theta was 0 to pi over 4. So if I'm saying u has to be tangent theta, well, tangent of 0 is 0, so u would be 0 as well, and then tangent of pi over 4 is 1. So that's nice, 0 to 1. On the other hand, this integral would have been something like 1 over w to the 5th dw, where we're taking w to be, write it over here, w is cosine theta, dw is negative sine theta d theta. So to actually write that, I need to make it negative. Yeah, just put it there. Cool. And then, again, be careful. Theta went from 0 to pi over 4. That would make w go from, well, cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. So that's a little uglier. Let me just copy this one down. Okay. Let me just erase this. Negative 1 over w to the 5th is negative w to the negative 5. So that integrates to negative w to the negative 4 over negative 4. I guess the negatives cancel. So what did I say? 4w to the 4th on the bottom. Does that work? Negative w to the negative 4 over negative 4. Yes, good. Then this is u squared over 2, 0 to 1. Great. So this works out nice. This is 1 over, well, w to the 4th, if I plug in root 2 over 2, that becomes, well, squaring it would give me 2 over 4, so a half. Squaring that would give me a quarter. So that's 4 times a quarter, which is 1. So that's just 1, actually. That's nice. Minus what I get if I plug in 1. And then over here you get just 1/2. So that's 3/4 minus a half is a quarter. Again, can't believe that works out that nicely. Hopefully I didn't make a mistake. Let's proceed. 47. I immediately see everything has a secant, so cross out one secant from every term. And hope it's nicer. It would look like that. And then I think to myself, I hate secant theta minus 1, but I love, secant squared minus 1. So what if I multiply by the conjugate? Secant plus 1. So that gives me secant tangent on top, which is sort of nice. Forgot my theta. Plus just tangent theta. And then on the bottom, difference of squares gives me secant squared minus 1 as desired. But secant squared minus 1 is just tangent squared, assuming I'm remembering that identity correctly. Right, secant squared minus 1 equals tan squared. Because if I multiply everything through by cosine, I get 1... Wait, if I multiply everything through by... Yeah, 1 minus cosine squared equals sine squared, which is a true fact. So that is correct. Talking to myself a little bit. Then the question is, can we handle that? Yeah. Now the tangents kind of go away, at least some of them do. So this is... Yeah. Oh. Did I just make it uglier? Well, let's see. Let's see. That's secant theta plus 1 over tangent theta. So I've sort of flipped things from where they were here. That's sort of a weird fact that worked out that way. Kind of absurd. But maybe this one's nicer, right? In the sense that you can split this one apart where you couldn't split the other one apart. Right, so I'll write down two integrals. Secant over tangent is 1 over cosine over sine over cosine. Flip it and you get just a cosecant, I think. The other one's 1 over tangent, which is cotangent. And then, are these nice? Maybe. I don't know. I have to look these up. I don't know if I remember these. Okay, so I looked up one of them. This is considered a standard integral in the sense that it's too hard, so they just give it to you. And then this one, you can actually do the cotangent integral just fine, I think, with a u sub, right? Cotangent is cosine over sine. And then you're like, pick u as sine theta. So du is cosine. Don't even need to correct any terms. This is just 1 over u du, which integrates to natural log of u. Plug back in, you get natural log of sine. So that's natural log of sine of theta. Yeah, and theta is fine because we started with it in terms of theta, so that should be correct. Great. Number 49. This immediately screams integration by parts, just because I have like this thing which I can set as u and this as dv. Do I want to integrate tangent squared? Maybe. I mean, let's see what happens. U equals theta. dv is tan squared theta. d theta. So du is d theta. V, it's a little annoying. V should be the integral of dv. So that's the integral of tan squared. I don't want to write that as sine squared over cosine squared necessarily. That doesn't really help. Maybe I do, yeah, this should work. Tangent squared is secant squared minus 1. And then antiderivative of secant squared, you say, okay, what function gives me secant squared as derivative? The answer is tangent. So that's tangent theta minus theta plus c. Of course, we don't need the plus c. I'll just put tan theta minus theta. Then doing the whole integration by parts procedure, uv minus integral v du turns out to be theta tan theta minus theta squared for uv minus, yeah, this will be doable, minus v du is just this. So this turns out to be, I'll leave this term alone. Integral of tangent is very similar to what we did above. I think you just get a natural log of cosine, maybe negative natural log of cosine. But it's a u sub. Let's do it really quickly. Tan theta d theta, write it as sine over cosine. Do a u sub with this is u. So then du would be negative sine, so I correct for that. It's 1 over u, and you get negative natural log of u, but u is cosine. So there you go. That's the result. So negative and negative becomes a plus. Log absolute value cosine theta. Then just integrate this guy. Again, minus and minus becomes a plus. Integral of theta is theta squared over 2. You can simplify, but who cares? That's your answer. 51, making good progress. Things actually didn't seem so bad for a while there. Let's see if this is worse. Anytime I see a square root, I think, can I do a clever u sub? The x cubed would be a problem, but maybe I can get away with this. X cubed is root x to the 6th, right? Root x is the 1/2 power, 1/2 times 6 is 3, so there you go. And then can I do a u sub? So I pick u equals root x. It's so nice. I mean, it's annoying when you don't know the trick, but it's nice once you've seen the trick enough. Because like you do the same thing as always. You say, well, solve for dx. That's 2 root x dx. But root x is u, so that's 2... sorry, I meant to write du here. du. So, writing this all out, I missed a dx here. Root x is u, that goes here. It also goes here. and then dx is 2u du. Plugging that all in, you get u over 1 plus u to the 6th times du, 2u du. So this becomes, pull the 2 out, multiply the u by the other u, you get this. Might need another sub. Right, this is almost something nice, but maybe I want this to be 1 plus w cubed? No. W squared? Yeah. So I could make the sub here of w equals u cubed to get, well, dw is some multiple of u squared. So, right, you need a factor of a third to correct things, but this u squared du is now 1/3 dw. So that works. Just double checking. Yeah. Good. Good. Then this turns out to be, pull out the 1/3. And then integral of 1 over 1 plus w squared. That's arctan of w. Of course, plug back in for w. W was u cubed, but u was square root of x. So it's actually w is u cubed, but that's this cubed, so that's x to the 3/2. So I could say this is 2/3 arctan x to the 3/2 plus c. Okay, that worked out. The next one is also a square root problem, so I'm tempted to do a similar thing. I'm also tempted to try multiplying by a conjugate. I wonder which will work better. I think multiplying by the conjugate's messier than I need it to be. Just pick. Oh no, it might be okay. That'll be 1 plus u. Try the whole thing as u. Try the whole denominator. Du still ends up being 1 over 2 root x dx. So dx, if you solve for it, is 2 root x du, but root x is u minus 1, so this is 2u minus 1 du. Let's just write it and see what happens. I need to address what x is going to be. We know what square root of x is, so x would be u minus 1 squared. I'm not sure if this will work nicely. So that's a u minus 1 squared. 1 plus root x is just u. Dx is 2u minus... Yeah, it might work out nicely, huh? Maybe. 2u minus 1 du. Okay, so pull the 2 out. You actually have a u minus 1 cubed over u. You simplify that integrand. And I mean, that's a little annoying, but we could make it work. Right, you could just sort of expand the top. You'll get u cubed, I hope I remember this correctly, minus 3u squared plus 3u minus 1 over u. And then you can break it up into multiple integrals, right? This is 2, let's just put it in parentheses. U cubed over u is u squared. 3u squared over u is just 3u. 3u over u is just 3. And then you get the minus 1 over u term. And you can integrate out all of those, right? That's u squared over 2. That's 3, or so, I meant to say u cubed over 3 for that. It's going too fast. This is 3u squared over 2. This is 3u. 1 over u integrates to natural log of u. Out of your constants, sorry. Went below the screen. Plug back in for u. U is just 1 plus root x. So, I mean, it's hideous. Whoops. 1 plus root x cubed over 3 minus 3 halves 1 plus root x squared minus 3 1 plus root x minus natural log of 1 plus root x. I hope that's right. I really, really hope that's right. Anyway, that idea works. Maybe other ideas, maybe multiplying by the conjugate would have been nicer in the end, but who knows. Maybe that even simplifies to something better, but I'll leave it like that. Future Troy here. This should have been a plus. Don't know where I got a minus from, right? It's just literally from right here. Apologies. 55. Negative exponents I immediately write as positive exponent in the denominator. Then I ask if a u sub works. Nearly. Oof, okay. Again, I don't want to distribute everything out. It'd be gross. Do I want the x minus 1 on top? So do u sub with u as x minus 1. Then x would be u plus 1. That might work out. So I just don't like the minus 1 being on the bottom. So maybe I say, make it a u. Then you don't have to subtract anything. Du is real simple. This becomes 1 over u to the 4th du. Then you just have to address what is x cubed. Well, from here, x is u plus 1, so x cubed is u plus 1 cubed. So that goes up here to fill in for the x cubed. And then the question is that nicer? And I think the answer is yes, just because, distributing all that garbage up top, or expanding all that garbage up top, gives you something like what we got in the previous problem. Unless there's a quicker way to do this. Maybe not, though. And then you kind of just crush it by splitting it into 4 integrals. I'm not going to bother. You can do that. That should be fine. Yeah, that should be fine. So, good enough. 57. Weird. I mean, my brain is still on square roots from the previous, so this is exceptionally weird, but what if I did that u sub? So du is 1 over 2 times that square root times the derivative is a 4, so you get a 2 on top, I believe. Check that, of course. So this would be... I still need to address what x is. But you can solve the u equation. Say u squared would be 4x plus 1. So x would be... Oh, this is getting ugly. Would be that. But let's just see. Ugly doesn't mean bad. Let's even solve this first. So dx would be 1/2 root 4x plus 1 du. But 4x plus 1 under a square root, that's u. So this is half u du. So plugging everything in, the x on the bottom is u squared minus 1 over 4. The square root of 4x plus 1 is u. So I didn't need this much space, but oh well. The du, or the dx is 1/2 u du. Let's put that up top. So we get cancellation. And this looks like just that, huh? 4 over 2 times that is 2 over that. And that is rather nice. We've seen one like this already. You would have to split this apart and do partial fractions. Right? Difference of squares gets you there. And I don't know if I can do this one off the top of my head, but you could say that this is going to be some number over u minus 1 plus some number over u plus 1. Multiply across by the big denominator and say that's a u minus 1, b u plus 1, or did I do it wrong? Minus 1 plus 1. There we go. And then if I plug in smart values of u, say I plug in 1, then I would get a equals 1. If I plug in -1, I should get b as -1. I probably could have come up with that as a guess, but anyway. That is, so a over u minus 1 plus b over u plus 1 du. Integrate that, you get this, just from memory. Plug back in for u was the square root thing. Plus natural log of the square root thing plus 1 with a constant. Ugly, but should be correct, I think. Another plus-minus mix-up from future Troy. This should have been a minus. Forgot to carry it through. It's happening a lot. Anyway, and then you can carry it through to the end here. Sorry about that. The next one looks very similar, but I have an x squared. And if I have an x squared, I'm thinking trig sub. I'm thinking almost trig sub. I'm thinking I want the x squared by itself to use a trig sub. So I could do this. I could sort of factor out the 4. So that's x squared plus a 4th. Right, convince yourself that works. But then the 4 can come out of the square root as a 2, so, and it's in the denominator, so let's just bring that out entirely as a 1/2. So this is now 1 over x root x squared plus a 4th. So my trig sub should be something like x equals 1/2 tan theta, I believe. Dx would be 1/2 secant theta when I take the, or secant squared theta when I take the derivative. So writing this out, let's see, let's put this up top. So dx is 1/2 secant squared theta d theta. X is 1/2 tan theta for that term. And then the square root is going to be 1/4 tan squared plus 1/4. So you factor out the 1/4, and then you have 1 plus tan squared is secant squared. So you have something like 1/4 secant squared. But that works out nicely, right? Square root of a 4th is 1/2. Square root of secant squared is secant. These halves cancel at the very least. And actually, I guess I could say this half and that 1/4 is really a half in the denominator. So I guess all the coefficients or all the constants cancel. And you're left with something like this. Secant squared theta. Just tangent squared, I guess? Or sorry, not tangent squared, whoops. Tangent, secant. So I'll write secant tangent. Square root of secant squared is secant. We still have the tangent. We still have the secant squared on top. One of those secants is going to cancel. So you get secant over tangent, and this is where I think convert that bad boy to sines and cosines, right? 1 over cosine over cosine is 1 over cosine times cosine over sine. That's the integral of cosecant. And I'll just say that's one you look up, right? We saw that one before. Maybe I still have it up here. I don't remember it off the top of my head. Yeah, so it's negative natural log cosecant plus cotangent. Of course, you still have to convert back to the world of x's, for which you should draw a right triangle. Right triangle that obeys this thing, which is to say you want tangent of theta equal to 2x. So let's be a little careful. Yeah, no, that would be fine. Tangent is opposite over adjacent. Take the adjacent to be 1, why not? So that would have to be 2x over 1, right? And then this is square root of 4x squared plus 1, which is glorious, right? That matches that. So you can figure out cosecant and cotangent from there. I've sort of run out of room, but cosecant's 1 over sine, so it's hypotenuse over opposite. You can just draw from the triangle. Sorry, I was blocking it. Cotangent is cosine over sine, or it's 1 over tangent, so it's adjacent over opposite. So you can figure that out. Number 63. Oh, another square root. And we just hit the 2-hour mark. What to do? I could factor the x out of both terms in the denominator and be left with x times 1 plus root x. And a u sub might work. It really might. Let's try it and see. Basically, whenever I see a square root, I think, give it a shot, you know? Try u sub. Try u equals root x. Or 1 plus root x is maybe better. Maybe both work. Who knows? Du would be this. Same trick as always. Solve for dx, and that becomes 2 root x du. Root x, though, is u minus 1, so that's 2u minus 1 du. And we're also going to need x, right? X appears here, but you can just get that by squaring this expression. So putting all the pieces together, you have the integral of 1 over x is u minus 1 squared. 1 plus root x is just u. dx is 2 times u minus 1 dx. The u minus 1's sort of cancel, so pull the 2 out, be left with 1 over u times u minus 1. And again, integrate by partial fractions, right? This looks like 2 integral of 1 over u minus 1 minus 1 over u. Let's just double check that. I think that's right. Then you get 2 natural log of u minus 1 minus natural log of u. Maybe rewrite that as just 2 natural log of a quotient. This is looking very similar to a previous problem. Write it as nicely as I can, and then plug back in for u. U was 1 plus root x. Ta-da. Okay, so square root shows up, pick it for you, and hope for the best. 65. 65. C is some arbitrary number, and I don't like having it under a cube root. So yeah. The thing to always do is just shift it out. Do a u sub. Du is then dx. And this x term can be solved for. You're like, well, x is just u minus c. So I shift the c out. Right? This becomes x is u minus c. And now I just have the cube root of u. So u to the 1/3 du. And this is pretty standard at this point. U times u to the 1/3 is u to the 4/3. Let's put parentheses. Minus c u to the 1/3 du. U to the 4/3, if I add 1 to it, I get 7/3. Divided by 7/3, so multiply by 3/7. Minus c u to the 4/3 over 4/3, so 3/4 c u to the 4/3. Finally, plug back in for u. U is just x plus c. Don't forget your constant, which I'm writing as a big C instead of a little c. Cool. 67 almost looks nice. Again, the strategy is say what you don't like about the integral and then try to fix it. I mean, it would be nice... Actually, yeah, it would be nice if squares were around instead of fourth powers, of course. And you can actually get squares by factoring it, right? It's a difference of squares. It's x squared minus 4, x squared plus 4. The x squared minus 4 is another difference of squares. It's x minus 2, x plus 2, x squared plus 4. I can't really split apart x squared plus 4 unless I use complex numbers, but I won't do that. This turns out to be... So doing partial fractions, it's going to be a little ugly. But it's worth it. You get a linear term here, you get another linear term here. Then you have a quadratic, so you need to put a linear cx plus d on top. That gives you a, or 1 equals a times x plus 2 times x squared plus 4 plus b times x minus 2 x squared plus 4 plus cx plus d x minus 2x plus 2. Truly hideous. There aren't, I mean, you can plug in nice values of x to determine some of these unknown coefficients, a, b, c, d, but probably not all of them. But let's see what we can get, you know. Actually, no. If I plug in 2... Yeah, I can plug in 2 and be safe. 2 will cancel out everything here, because there's x minus 2 in each of those. And that's saying 1 equals a times 4 times 8. Wow, okay. So a is 1 over 32. Hope that's right. Try x equals negative 2 next. Right, that should... Well, that cancels out everything. That would be unfortunate, wouldn't it? Or does it cancel out everything? Yeah, it does, doesn't it? No, it doesn't cancel out everything. It doesn't quite cancel out enough, but let's see. That would give us 1 equals a times 0. Yeah, no, it does work. It does work. Okay. Plus b times negative 4 times 8. So that's negative 32b. So b is negative 1 over 32. Very similar. I think that those are the only ones I'll figure out that way. So let's rewrite this now. 1 equals, we know some coefficients. Use that for A. B is minus 1 over 32, so we'll use that. And then we don't know C and D yet, but we can figure them out. Don't worry. I mean, I'm tempted to plug in 0 as well. That might be nice. Let's just see what happens if at this point we plug in 0. Right, if we plug in 0, we get 1 over 32 times 2 times 4, so that's 1 over 32 times 6. So this is 1 equals 6 over 32 minus negative 2 times 4. Oh, sorry, why did I say 6 before? It's because I'm tired. It should have been an 8. Negative will give you a plus another 8 over 32, I believe. Okay. And then plug in 0 here. The C goes away. So it's just D times negative 2 times positive 2. So that's minus 4D. Okay. 8 over 32 is 1/4. So 1/4 plus 1/4 is a half. Subtract the half from both sides. You get a half equals negative 4D. So D equals negative 1/8. That's nice. And now we should be able to determine C by plugging in anything. Right, at this point we have, let's plug in what we know for D. This is usually much further than we need to take these sorts of things, but bear with me. So I copied it, and then we're going to paste in D here. And then, I don't know, we plug in 1 or something. If x equals 1. What do we get? We get the equation 1 equals 3 times 5 is 15 over 32. If I plug in 1 here, I get negative 1, so the negatives cancel. 5 over 32. If I plug in 1 to these bits, I get negative 1 times 3 is negative 3. That's negative 3 C minus an eighth. Okay. 15 30 seconds plus 5 30 seconds is 20 30 seconds. Which I mean is 10 16ths, which is 5 eighths. Subtract that over, you get 3 eighths. Divide by negative 3, or divide by 3, you get 1 eighth. You can do the algebra, so I'm sort of jumping around really quickly. Equals 1 eighth minus C. Oh, does C just end up being 0 then? That would be nice. I'm going to check this, because this is absurd. One sec. Astonishingly, all that work is correct. So you get, this integral turns out to be, plugging everything we know in here, A is 1 over 32, B is negative 1 over 32, C is 0, so Cx just doesn't come up, and then D is negative an eighth. And then that's nice to integrate. That's 1 over 32 log absolute value x minus 2 minus 1 over 32 log absolute value x plus 2 minus, that looks like an arctan, right? You can bring the 1/8 out, and then you'd get an extra 1/2 because of the 4 in the denominator. arctan x over 2. Ta-da! So the hard part is definitely the algebra. Next one, 70, yeah. There was a 69, but it used hyperbolic functions, and I'm just not going to worry about those. C a square root, B a square root. U equals root x. Du. 1 over 2 root x dx. Same thing we always do. That means dx is 2u du. Skipping one step there, but we've seen it enough. This should be now the integral of u, e to the u, times 2u du. That's 2u, let's pull the 2 out. U squared e to the u. Perfect example of integration by parts that we can use a table for. That is really wide. Differentiate repeatedly, integrate repeatedly, draw some diagonals, do plus minus plus, answer equals 2 times the quantity, follow the diagonals, u squared e to the u minus 2u e to the u plus 2e to the u plus c, plug back in for u. U squared would be square root of x squared, so that's just x. Then e to the root x minus 2 root x, e to the root x plus 2e to the root x plus c. Whew, that was fun. 73 looks not fun. Cosine to the 4th, huh? You're going to hit me with one of those. If it was 1 minus cosine to the 4th, I'd try to split it apart as difference of squares and then do some trig identities. We have a we have a sine of 2x. That's 2 sine x cosine x. That's a trig identity. Let's see how that helps us, though. Is 73 gonna stump me? I guess I could plug in an identity for cosine squared and square it to get cosine to the 4th. Actually, that's not bad, because that gets a 2x in the cosine. So we'll leave it as sine of 2x. And then the denominator becomes 1 plus... I should have made more room for myself. One plus cosine squared squared, but cosine squared can be replaced with 1/2 1 plus. Still didn't make enough room. One half 1 plus cosine 2x. I mean, I don't have high hopes for this, but let's see. That will be 1 plus 2 cosine squared plus, or no, 1 plus 2 cosine, and then there's a half. Let's just work this out. Annoying. The 1/2 squared will be a 1/4, and then all this squared will be 1 plus 2 cosine 2x plus cosine squared 2x. So that is 1 plus a 4th is 5/4. Plus a 4th times 2 is a half. Cosine 2x. Plus a 4th times cosine squared 2x. That's in the denominator. I truly, truly hate that. Unless I can complete the square. Wouldn't that be insane? Wouldn't that be truly monumentally, absolutely insane? Let's call 1/2 2/4. So I can factor a 1/4 out of everything. And it'll be in the denominator, so it'll come out as a 4. And then this is, let's write it backwards, cosine squared 2x plus, I factored the 4 out, so there's still a 2. Make more room again. I didn't need that much room, actually. That was fine. Plus 5. Okay. Hopefully the algebra's right. I mean, who knows at this point? We're 2.5 hours in. But if I can complete the square on that quadratic, my hair is getting crazier and crazier. If I can complete the square on that quadratic, I might have something. Because then maybe a u sub works or something like that. So, I mean, let's hope. Let's hope. Right? So again, sidebar. Let's complete the square down here. That's going to be cosine of 2x plus something squared, and then plus some other garbage. It just needs to be plus 1, because then you get your cosine squared and you get your 2 cosine 2x. But that plus 1 needs to be a plus 5, so you get a plus 4. This might work. Then, so you could plug that into the integral now, or you could make a u sub at this point. You could say u is this whole thing. So u is cosine 2x plus 1 plus du is, just chain rule it, right? -1/2, or sorry, -2 sine 2x dx. And that's glorious because this guy is this. I'm amazed this worked out, to be quite honest. Of course, we have a -1/2 that we need to account for, so divide by -2. There's already a 4, so that will be, we should just have a -2 hang around. And then on the bottom, this is now u squared plus 4. We already said that's the remaining pieces are du. Yep, that works. And then that is an arctan. Because of the 4, you'll have a 1/2. So it'll cancel with the 2, and you'll just get negative arctan of u over 2. Plug back in for u. What was u? U was cosine 2x plus 1. This is worth checking with a derivative calculation, because that was truly absurd. Derivative of this thing. Well, derivative of arctan with the negative out front will be 1 over this thing that's inside of it times the derivative of that thing, and the derivative of that is 1/2. Let's just go ahead and put it on top. 1/2. Derivative of cosine 2x is -2, so the negative will go away. -2, so positive 2, so even the 1/2 goes away, I suppose. Well, let's just write it all out. I won't skip steps. -2 sine 2x. The derivative of 1 is 0. Times, right, that was the derivative of this. Is that enough? Maybe. Did I do that correctly? Hopefully. 1 over... sorry, this thing was supposed to be... arctan is 1 plus this squared. Times derivative of what's in the parentheses. And where did the 1/2 come from? Oh, it came from there. Derivative of that's that. That's good. So this becomes, the negatives cancel, the 2 and the 1/2 cancel. You get your sine of 2x on top, which is wonderful. And then this is, should be exactly what you need. Maybe you need a trig identity to work it out. But a whole bunch of stuff over 4. Cosine squared plus 2 cosine 2x plus 1. Yeah, okay, so hard to check this way because you need a trig identity, but maybe I'll check off screen real quick. Yeah, so it's good. You can even simplify your answer even more, which I noticed once I plugged it into an integral solver. You can write it like this. Cosine 2x plus 1 over 2. That's the same identity we used here. That's cosine squared. So it would have been easier if I took a derivative of that thing, because that would have been, negative 1 over 1 plus cosine to the 4th times the derivative of cosine squared, which is 2 sine cosine, which is sine of 2x, and then, well, a negative would cancel as well. But that works. Next one. This time maybe u equals square root of x doesn't work. But if I see square roots and a plus, I think multiply by the conjugate. Root x plus 1 minus root x is the conjugate. And simplify, the top stays the same, of course. Bottom is a difference of squares. Root x plus 1 times itself is x plus 1. Root x times itself with a minus sign is just x. That's absurdly nice. The bottom goes away, it's just 1. So algebraic simplification helps a lot here. Kind of cool. And then u sub, right? So do each of those separately, I suppose. So u equals x plus 1, du is dx. This would be, u to the 1/2 du minus, I don't need the u sub here, it's just x to the 1/2 du. So these are basically the same, 2/3 u to the 3/2, but u is x plus 1, minus 2/3 x to the 3/2 plus c. Great. 77. Trig sub, probably. That looks like a tangent trig sub. X equals tan theta. Dx equals secant squared theta d theta. Could change our bounds if we want. Right, initially x was 1 to root 3. So you get the equation 1 equals tan theta. So what value of theta has tangent equal to 1? Well, pi over 4 does. And then what theta gives you tangent equal to root 3? Tangent is sine over cosine. So you want the sine to be root 3 over 2, and the cosine to be 1/2. That's tall, that's pi over 3, I believe. Because sine of pi over 3 is root 3 over 2, divide by 1/2 for the cosine, you get root 3. Good. Cool. So new bounds, pi over 4 to pi over 3. 1 plus x squared is 1 plus tan squared. That's secant squared, but it's under a square root, so it's just secant. We also have the dx is another 2 secants, so I'll call it secant cubed on top. X squared on bottom is going to be tan squared. that one doesn't look too bad. Let's see if looks are deceiving. Don't want to convert to sines and cosines. Might do secant squared trig identity. So secant squared is what? Tan squared minus 1? Then maybe split the integral in two. You get single secant, which we can handle. And you get secant over tangent squared, which you can probably handle. Yeah, so splitting this apart, and like simplifying, so tan squared times secant divided by tan squared is just secant. Then the second part of the integral would be just minus, so it's a minus sign, secant over tangent. But secant over tangent is 1 over cosine over sine squared over cosine squared. Just cosine over sine squared, I think, when you simplify it, which is a great U sub problem. So here we get, again, this is when you remember secant plus tangent, I think. I say you remember, and then I'm not sure if I remember. Worth checking, why not? Integral of secant. Yep, that's right. Great. And then this you do a sneaky little U sub on. Oh, I should have put my bounds on here. Well, they'll have the same bounds. Let's keep it all together in one. Sneaky U sub, that's 1 over U squared du. That's U to the negative 2 du. That integrates to U to the negative 1 over negative 1, but there's already a negative, so that's 1 over U. And U is sine, so that's 1 over sine. I'm not even going to write that as cosecant because that would be annoying. And then you plug in a bunch of stuff, right? So maybe we'll do it. Secant of pi over 3 is 1 over cosine of pi over 3. But cosine of pi over 3 is a half, so secant would be, the reciprocal of that would be 2. Oh, but I forgot the plus tangent. So secant, so secant of theta is 2. Tangent of pi over 3, didn't we already say that? That was root 3. So you get log of 2 plus root 3. Don't need the absolute value, really. Minus 1 over sine of pi over 3 is root 3 over 2. So reciprocal. Then subtract what you get if you plug in pi over 4. Secant of pi over 4 is 1 over cosine of pi over 4, but that's 1 over root 2 over 2, which is 2 over root 2. I'm not going to rationalize these denominators. Tan of pi over 4 is 1. And then you subtract what you get from subtracting this. So that's plus sine of pi over 4 is root 2 over 2. Really hope that's correct. There's no good way to check really quickly, but there you go. Actually, I can check. I'll pause. Great. So it's correct, except this last term, I just wrote it backwards. It should have been 2 over root 2. So great. 2 over root 2. Done. Oh, getting up there. This looks like a good one. This one you can probably say u is 1 plus e to the x. Do a sneaky u sub. The reason that's good is because this is really e to the 2x is e to the x times itself. Right? So this e to the x dx is just du. This e to the x can be written as u minus 1. So this becomes integral u minus 1. The bottom is just u, of course, du. And that's nice, right? That is just split apart the fraction. That's 1 minus 1 over u du, which comes out to be integrate 1, you get u. Integrate 1 over u, you get natural log absolute value of u. Tack on a constant, plug back in for u. u is 1 plus e to the x. Don't really need the absolute value, but oh well. Done. 81's nice. Right, because the derivative of arcsine is 1 over the square root of 1 minus x squared. So u equals 1 plus arcsine. They're throwing us softballs now. Kind of nice. At least I hope I'm remembering that derivative correctly, but if so, this is just the integral of u du, which is u squared over 2, which is 1/2, 1 plus arcsine, just plug back in for u, squaring it, plus a constant. Cool. I'm almost scared by how easy that was. We'll trust our gut. Past Troy was correct to be suspicious of this one. I actually wrote down the integrand wrong. So this problem is actually x plus arcsine x over root 1 minus x squared dx, which is pretty much the same difficulty level. You would just have to split it into two integrals, right? So you'd be like x over root 1 minus x squared. That's a u sub. And then very similar to what we did, except we'd take u to be just arcsine x here instead of 1 plus arcsine x. But if you want to do that, you know, our u on this integral would be 1 minus 2x. So du is negative 2 dx. So over here, I would just have a negative 1/2 to balance things out. And then this would have been, sorry, brain fried. 1 minus x squared for u, and then negative 2x dx. Cool. So that gives us the x dx. And this is u to the negative 1/2 du. On this side, I'll just reuse the variable u, why not? Pick it to be arcsine x, so very similar to what we just did. You get 1 over root 1 minus x squared dx. So this integrand becomes no terms to balance out. It's just u du, very similar to the problem in blue that I miswrote. And so this ends up being integrate the first one, and you get u to the 1/2 over 1/2. So the 1/2 in the denominator comes up as a 2, cancels the existing 1/2, but it's still negative. So you get negative square root u. And then just like last time, u squared over 2 plus c. And if you plug back in, I guess I need to be careful. I have two different u's floating around. This first u came from 1 minus x squared. So that's negative root 1 minus x squared. This second u, which maybe I should have called u tilde, was arcsine. So that's 1/2 arcsine squared, just like before, plus c. And blocking it, but we're done. Oh. That looks hard. So, okay, thought process. I know that the antiderivative of, yeah, I know the antiderivative of log x is actually that denominator, so that's just pattern recognition. Plus c is, we don't need it, but whatever, to be precise. So, if I'm trying to go backwards, 1 over that. Well, how do we get 1 over that? Probably, probably a log, right? Like, derivative of log is 1 over something. So, do I try log of one of those things? Let's make guesses. Right? Let's make some big guesses. What if our answer is log x? It's not. I know that. But, you know, that would mean this is our answer. And then let's see if we can just patch it up. Right, so the derivative there would have been 1 over log x times the derivative of log x, which is 1 over x log x, which is really darn close. So how would we get a minus x here? I mean, I guess you think, like, factor out the x, do log x minus 1. So do I do log of log x minus 1? This is not an integration technique, by the way. This is me guessing. Log of log x minus 1. Would it be 1 over log x minus 1 times the derivative of log x minus 1, but the derivative of log x minus 1 is just 1 over x. And that's 1 over x. Oh, that works. Oh. Sometimes pattern recognition goes a long way. Correctly guessed an antiderivative there. That's crazy. Sorry, that's log x minus 1 plus c. Right? Because derivative goes this way, integral goes that way. Awesome. I have no idea how you would actually integrate that. Honestly. Like... Okay, I mean, maybe we should do it. So just to say, like, you don't have to have crazy intuition like that. What if I picked, well, what if I wrote this as this, like we were just doing, and then I said that's u, so u is log x minus 1, du is 1 over x dx. That does it. Okay, so that's not actually that bad. I didn't need to go crazy mode. That's just 1 over u du, which is log absolute value of u, but u is log x minus 1. Okay, so same answer. I guess I was off by absolute value. But yeah, it's kind of cool, right? Next one. I think there are only like 5 left. X e to the x, 1 plus e to the x under a square root. Why not? Take the square root as u. So many u subs in this problem set. Who would have thought? Du is going to be 1 over, well, not 1 over, but something over the square root of that. Derivative of 1 plus e to the x goes up top by chain rule. And that looks right. Cool. Solve for dx? Maybe? Why not? Don't know if this will work. Dx. Or solve for e to the x dx. We got an e to the x dx here. We want it in terms of u. So e to the x dx is just 2, yeah, it works. 1 plus e to the x under a square root du, but that square root is u. So la-di-da, that sort of always happens with these problems. And that's almost everything we need. We also need x. So maybe I solve from here and say u squared is 1 plus e to the x. U squared minus 1 is e to the x. Take a natural log, maybe. So x is natural log of x squared minus 1. Don't have high hopes anymore, but let's plug it in and see. So on top you have natural log x squared minus 1. That handles that. Then e to the x dx is 2u du. Put the du out here. And then this piece is just u. So, oh. Well, look at that. The u's cancel. Great. That's what I was worried about. So the 2 comes out. You want to integrate this guy. Wait, why did I have x? I shouldn't have had x. Yeah. Okay, that was just a typo here. That's u squared minus 1, not x squared minus 1, so that's a u. Let's erase it and rewrite it. Okay, it doesn't affect anything, I just wrote u instead of x. Same story here. How do you integrate that? Oh, that is nice. U squared minus 1 is u minus 1 times u plus 1, difference of squares. So you have a product inside the log, which turns into a sum of logs. Log u plus 1, log u minus 1. Yeah, that works. And then each of those should be somewhat nice. I mean, I guess you do a little substitution, say w equals u plus 1 or w equals u minus 1, but at the end of the day you should get this, because du won't impact anything. Yeah, it should just be, you know, just like integral of ln x is x ln x minus x. This will be u plus 1 ln u plus 1 minus u plus 1. Same story for the next one. U minus 1 ln u minus 1 minus u minus 1 plus c. And it simplifies, of course. And you can plug back in for u. But wouldn't that just be ugly? Let's leave it like that. We're happy with that solution. I mean, I wouldn't be happy with it on an exam, but for a video that's almost 3 hours long, I'm happy with it. I was really hoping we wouldn't get more trig. Maybe replace the sine squared with 1 minus cosine squared. And then maybe split it apart into two integrals, do integration by parts. Is there a better solution? Maybe straight up integration by parts? Yeah, let's try straight up integration by parts. U is x, dv is the rest of it. Because I can integrate that expression, the sine squared times cosine. And of course I can differentiate x to get dx. The integral of sine squared cosine squared, or sine squared cosine, just pick u as, or pick whatever substitution you want to name it, to be sine. So it's u squared du, and then that's u cubed over 3 du, so you get sine cubed over 3. Again, going fast because who has time for this? And then you could check, take the derivative to make sure it's right, and you get sine squared cosine. Yeah, it works. So this equals uv 1/3 x sine cubed x minus integral v du. And maybe I've tied myself in knots here, but maybe not. Let's forget the parentheses. That integral should be doable, right? That's fairly standard. So pull the 1/3 out. Sine cubed, I could pull out a sine squared as 1 minus cosine squared. So I leave one sine, and then I do another u substitution type thing, or call it w substitution. Pick that as w. Sorry, do I pick the whole thing as w? I guess I wouldn't want to pick the whole thing as w. I guess I would want to split this into two integrals and then do a sub. Yeah, so minus 1/3 integral of just, 1 times sine. That one's nice. And then plus 1/3 cosine squared sine under the integral. Okay, so then you can sub in w equals cosine x or something. You'll get this. Integral of sine is negative cosine, so the negative becomes positive. Cosine x. And then let's just do it really quick. u is cosine, du is negative sine, so I'm off by a negative. Let's fix it. And then u squared du integrates to u cubed over 3, so I'll get another 3 on the bottom. That's a 9. And our u is cosine. And that works out pretty nice. Great. 89. I mean, who knows? Multiply by conjugate? What else are we going to do, right? So this is like 1 minus sine x over 1 times 1 plus sine x under the square root over itself. Does that turn out nice? The top becomes kind of good, right? That's difference of squares, 1 minus sine squared. So that's going to give me a cosine squared under the square root eventually. That's good. And then this is still 1 plus sine. So totally fine. This is cosine x over that. And a u sub should finish us up. Pick what's under the square root. Du is then cosine x dx, which already appears in the integrand. So this is basically u to the negative 1/2 du that we're integrating. Yes, it is. And that integrates to u to the positive 1/2 over 1/2, which is 2 root u, which is 2 square root 1 plus sine x plus c. Great. Into the 90s. Yeah, we just have 2 more. That looks insane. I really hated writing that because I have no idea how to do it. Multiply by conjugate? I mean, let's see what that looks like. Oh, this is ugly. They're like reciprocals of each other. But I would have to do... I mean, maybe I multiply by root 9 minus x over itself. Or 9 plus x, maybe. No idea if that's good. It's probably not, honestly. What does that become? That becomes something truly insane. I guess I can just write one big square root. 9 minus x times 9 plus x is 81 minus x squared. And then you get under the square root 9, oh, this is ugly. And then sort of the inverse, maybe, for the next one. But is that good? No, it's really not. Do you handle them separately? Do you split into 2 integrals? I mean, how would you solve one of them? I guess multiplying by the conjugate on a single one? Yeah, let's just see what a single one looks like, if that's doable. So, okay, I have to stare at this for a second. I guess that would look like a trig sub if I do that. Or would it? Not really. This is a monster. Wow. There's gotta be a way to simplify this. Or do I just do u sub? I mean, do I become a crazy person? Do I say u is this? like I've been doing. So du is... I mean, this is what a crazy person would do. But it is problem 91. Okay, so chain rule it. Derivative of that, I'd have to use quotient rule, but I guess I can simplify a bit and make it negative 9 over x squared when I take the derivative, right? Because it's 9 over x minus 1, so 9 over x, yeah. Is that good? That becomes, let's put the constants out front, negative 9 halves. Lord, okay. I guess the square root flips then. And then what about the x squared? I guess I could put that a number of places. Let's put it here. Is that right? Oh, is that right? Negative 9 over 2x squared, yeah, dx. Is that a good thing? Maybe? I doubt it. Solve for dx. Dx equals, if I divide by this, it's the same as multiplying by u. Let's keep this over here. So that's u du. Is that right? Yeah. U du equals that. Good. How do I get rid of the x squared is the next question. I don't have high hopes for fiddling with this, but u squared equals 9 minus x over x equals 9 over x minus 1. Add the 1. It's 9 over x. Move some pieces around. X equals 9 over u squared plus 1. You can solve for x. And then x squared. Okay. So solving for dx here, it should be negative 2/9. X squared is going to be 9 over u squared plus 1 whole thing squared. And we still have the u du. Oh, if this works, I can't even imagine, honestly. One of the 9s will cancel. So you'll have negative 18 u, put that up top, u squared plus 1 squared. Yeah, looks good. So, and actually this piece is 1 over u. So this becomes, I don't know the bounds yet. The integrand is u minus 1 over u. And then I just need to toss dx on here. So let's do that. I'll pull the negative 18 out. And the remaining terms are just u over u squared plus 1 squared du. The question is this even solvable before I even figure out the bounds? Leave it blank for now. Maybe. Maybe, right? This looks like So u times that is u squared over u squared plus 1 squared. This times u, well, they cancel each other out, so that's minus 1 over u squared plus 1 squared du. Let's make some room for ourselves and erase some of this junk. Is it solvable? I guess I could combine the two integrals. I mean, can you do partial fractions here? Or do you just brute force it some other way? I don't see another way. Right? I mean, combine these, right? Why not? Who needs the parentheses? That was just u squared minus 1. Still don't know the bounds. And then I say to myself, can I write this? I don't know if it's smart, but can I write it as ax plus b, raise this to the first power, plus cx plus d, raise it to the second power? I want there to be a nicer way than doing that. As we hit the 3-hour mark. But I mean, I guess we'll see. Ax plus b times u squared plus... No, this isn't going to work. Stuff like this never works, right? Because you just get a cx plus d out there. And then you're like, yeah, a is 0, b is 1, c is 0, d is 0. Who cares? So, okay, let's not do that. Do I do a substitution? Maybe? U squared plus 1 is w. U squared minus 1 is w minus 2. But then dw doesn't work out. Honestly, I'm just happy I got to here. This might be one that stumps me. Because it can't be a trig sub, can it? I mean, do we want to see? Do we want to say u is tan theta? Du is secant squared theta d theta? I'm so excited to be done, but let's give it the time it deserves. This would be negative 18. Definitely don't know the bounds now. U squared minus 1 is tan squared minus 1, which isn't pretty. But you have a secant squared tacked on, so maybe that'll help from here. U squared plus 1 is tan squared plus 1, which is secant squared, and then you square it, so it's secant to the 4th. So some of the secants cancel. You get tan squared minus 1. I always forget to write my thetas, I apologize. Over secant squared. That might be doable. What's tan squared over secant squared? Sine squared over cosine squared. Wow, okay, this works. Negative 18. break it up into two integrals. Tan squared over secant squared is sine squared over cosine squared over 1 over cosine squared. The cosine squareds cancel. You get a sine squared. Minus 1 over secant squared is cosine squared. That integral is solvable. Oh, is there a trig identity for sine squared minus cosine squared? That's easy enough to look up, I suppose. Maybe that'll make my life nicer. Let me just Google trig identities. Apologies, you're just watching a screen and not seeing what I'm looking up. What is, I swear I've seen one like that. Cosine squared minus sine squared is 1. Minus 2 sine squared, or 2 cosine squared minus 1. Good. So, this can be, so cosine squared minus sine squared, oh, is actually cosine 2 theta. So that's negative. Okay, trust me, a trig identity does this. And then, voila. Antiderivative of cosine 2 theta is 1/2 sine 2 theta, which is why I threw away the 36 and made it an 18. Oh man, if this is correct, I don't even know. We need to undo the trig sub, and then we need to undo the u sub, and then we need to plug in our bounds. Okay, undoing the trig sub, let's do that by writing sine of 2 theta as 2 sine theta cosine theta. So we're back to 36. Let's draw our triangle. That is not right. That's not a right triangle either. What's wrong? Right triangle. Good. Here's theta. Tangent theta needs to be u, so that's u over 1. So that's 1 minus u squared, which is that what I wanted? Oh, opposite over adjacent. Whoops. This should be 1. And this is u squared plus 1. That is what I wanted. Good. Sine is then opposite over hypotenuse, u over u squared plus 1, times cosine is adjacent over hypotenuse. So, and then u is that ugly square root, which is really hideous to plug in, but work with the hand you're dealt, I suppose. U is root 9 minus x over x. On the bottom, you have u squared plus 1 squared. U squared is 9 minus x over x. And it's u squared plus 1 squared. I mean, I think this is the answer. I think. Maybe you simplify it a bit more and you say, like the bottom can be simplified. 9 minus x over x plus x over x is just 9 over x. So it's 81 over x squared when you square it. And then you have this. And you get, flip it around, and you get 36 over 81 is 12 over 27 is 4 over 9. Put the x squared on top, and it looks like this. I mean, can I absorb that at all? If you're assuming positivity, you get something nice out of that? Because I could put that in as... Well, anyway, I mean... Missing the plus c, sorry. I think that's the answer. This one's worth checking. Okay, I found some typos. Let's go back and try to correct them. This should have been a square root. I was going way too fast there. Then from this step to this step, I don't think there's a factor of 2 missing, so that should still be an 18, and positive 18 now. But then integrating does get you, let's see, wait, where was I? So yeah, sine squared, that's 18. And then does this go to 9 then? Right, because it's 1/2 sine 2 theta. So the half decreases you from 18 to 9. And then, okay, so this is just 9. Sine theta cosine theta, so that's also 9. I forgot the square roots on these. So let's just erase the rest of this and figure it out from here, because I believe the rest is or everything before this was correct. So this should be 9u over, okay, the square roots combine to just give you that. And I think that's good. Then you can go in and replace u. We actually have a fun fact here. U squared plus 1, if you solve for it, is just 9 over x. So this is 9 over x down here. That's a little quicker way. 9u is, well, u is this guy, 9 minus x over x under a square root. Okay, so looks like we got some simplification here. The 9's cancel, and you're left with x root 9 minus x over x plus c. And I hope that's correct. I guess we can check, because actually, you know, all along the way, we had bounds on the integral. X went from 1 to 3. And now that I'm back in the world of x's, I can just plug that in here. 1 to 3. And I at least know what the number should be that comes out, so this will be a good sanity check. This will be, you know, 9 minus 3 over 3 minus 1 times 9 minus 1 over 1. So this is 3 root 2 minus root 8. Root 8 is 2 root 2. And you get root 2. Okay, I'm still off by a factor of 2. This should be 2 root 2. Where did I lose that, is the question. Okay, one sec. Oh, of course. Okay, so here it is. I forgot to put the 2 back in. Sine 2 theta is 2 sine cosine theta, so this goes back to 18. This goes back to 18. This 9 should also be an 18. It just propagates through. Apologies for the errors. And then instead of canceling, you get a 2. So this is 2 times 3 minus 2 times 1 there. And then that's 6 minus 2 root 8. So that's 6 minus 2 times 2 root 2, so 4 root 2, and that gives you 2 root 2, and that's the right answer. Okay, so there were some little trig problems that I messed up, because it's been 3 hours, but that's kind of astonishing. And difficult. Last problem. Hopefully this one's easier. I'd probably start this. I don't like the 2 hanging out in there. I could use a trig identity, but I don't think it would help, so I'd probably start with a little u sub. So I cancel out the 2 with a factor of 1/2. Let's not put bounds on yet. This will just be 1 plus sine u du. And I think we've done this one before. That almost exactly matches up with this, right? So to finish off, let's actually figure out our bounds, you know. Theta went from 0 to pi over 6, meaning u should go from 0 to pi over 3, which is fine. Right, we just cut it in half, basically. This should then be 1/2 integral 0 to pi over 3. Let's, you know, do the multiply by the conjugate thing again. It should work here as well. 1 minus sine u under the square root. And this becomes the following integral. On the bottom, we still have the square root, which we can handle with another substitution. On the top, you have square root of 1 minus sine squared. That's square root of cosine squared, which is cosine. And so now you make the substitution w is 1 minus sine u. dw is negative cosine u du. So you're off by a negative sign, so pull that out front. I guess you can change your bounds again. If, you know, u went from 0 to pi over 3, then w should go from 1 minus 0, which is 1, to 1 minus sine of pi. I don't want to change the bounds. We'll deal with it at the end. So I'll just put blanks here. This should then be the integral of, so we took the negative out already, and then it's u or w to the negative 1/2 dw, which is going to be, okay, negative 1/2. Integral of that is just 2 root w. Plug in our unknown bounds. That's just negative root w, but w is 1 minus sine u. Now I know the bounds in terms of u were 0 and pi over 3, so now we can plug those in. This should be, if I plug in 0, starting on the bottom, I get, well, sine of 0 is 0, square root of 1 is 1, so that's negative 1, so that's subtracting a negative 1, so I'll start with that. And then plugging in pi over 3, you get minus the square root of 1 minus sine of pi over 3 is root 3 over 2. Kind of an ugly answer to finish, but it is correct. Just checked. So yeah, there you go. 12 pages of integrals, about 50 of them. Hopefully all correct. I guess I'll check before posting this video. But, yeah, I hope this helped. I'm sorry it took 3 hours and 18 minutes. But at least you can jump around and pick out the ones you want. Thanks for watching. Bye.